then there's people like Eugene in the world who are trying to figure out better ways to deal with actual data. And there's a lot of evolution in that space too. So we've made a lot of steps forward, but we've still got a whole lot of issues that remain from the previous generation of technologies. So when you think about a relational database, a typical enterprise Java application, for example, you essentially get in a bunch of events. It can be transaction instructions, it can be events from sensors, whatever it is, and you go about implementing the business logic and persisting it into the database. And you then chuck away the event. It's gone. So your data is then representing this golden copy of your data. And this fundamentally makes these kind of systems not fault tolerant. The moment you've got a defect, the moment that you've got some kind of operational issue, you deploy something incorrectly, your database gets corrupted, and that's it. You can roll back to backups maybe, but auspiciously you can lose up to an hour, up to a day with the transactional data, downtime, all hands on deck, all the kind of things that we hate doing as developers, operational issues. So the previous generation of technologies promotes this kind of stuff. As far as the current generation of big data technologies, if you're not careful, you land up in exactly the same situation. So it's an operational issue, but it's also, you define up front in the relational database what your data structure is. So everyone gets in the room and they say, all right, this is what our enterprise data model is going to look like, and we define it, and that works very nicely for the next 6 months. But the moment someone comes up with a different query, it becomes extremely difficult to develop a relational database because that data structure is defined. And the original data that we used in order to populate that data structure is now gone. We kept the mutable state, we didn't keep the original immutable state, it's gone. Okay? And in the previous generation of technology that was necessary because we just didn't store all of the source events. But in the current state where we've got enough space to store all of the events, we're still going through the process of throwing away the immutable data, mutating it and storing mutable data. Okay? So a lot of the same issues we've always experienced will continue to perfect that. Right, so if you think about a large data application, just getting back to what are the typical solutions people use, replication, domain segregation, we create these enterprise data models, we have master data management, we've got these massive change control exercises, and systems will fall over and you still can't get the data we need to get it. We're playing with Node. Very cool. All right, so a lot of what people try to do is simply go, right, so we've got to solve this big data problem, so what we're going to do is we're going to say big data is Hadoop, and we're going to install Hadoop, and therefore we've got big data. But the fundamental paradigm, the way that we've approached architecting the system hasn't changed. The other approach is simply we're going to install HBase. But like I say, the fundamental approach hasn't changed. Right, so if you think about what would you like to have, I'm saying that there's problems with the way we're doing it right now. So what would you like to have as a set of properties around not only a big data system, but a data system in general? So, the obvious one is, when you invest in the technologies, you want it to support a wide range of use cases. Fundamentally fault tolerant. And what I mean by that is not only can it fail over in hardware failures, but it's fault tolerant to human beings. So defects, admin messes, etc. The system should be able to recover from these kind of things. And with the current model of mutable data, it simply can't. It needs to be scalable, it needs to be lowly latent, it needs to be able to deal with massive amounts of data. In the web scale, we're talking petabytes, and maybe it's a bit less in enterprise, but still hundreds of gigabytes is still quite an issue to deal with. You need to be able to deal with structured and unstructured data. Increasingly, people are realizing that the bulk of the business value is actually sitting in unstructured data. So you think about a CRM, it's a fairly well-structured data set, but the bulk of the notes and the bulk of the business value is sitting in free text that people are typing into the notes on the CRM. Yeah. So even though it's within a structured place, it's still unstructured data. Down to complexity, in terms of architecture, to say a lot of these systems are fundamentally complex. Think about something like Cassandra, like a NoSQL database. It's fundamentally a very complex thing. It's distributed state, it's real-time, simultaneous reads and writes. It's fundamentally a complex thing. So if your entire your entire architecture is based on complex things, you're fundamentally at risk. You're always going to be asking for trouble at some point, the moment that you've got too much complexity throughout your architecture. So one of the things you need to have to do is say, I'm aware that there's going to be a certain amount of complexity in my architecture, but I want to try and constrain that to certain places that I can manage. Okay? And the final point being the real key one is to say, you need to be able to get at different types of data. You need to view your data in different ways. And at the time that you first start your project or you first define your solution, you don't know what those queries are going to look like in 2 years' time, a year's time, in most cases not even 3 months' time. So the flexibility to be able to answer different kinds of questions without having to know what those questions are up front. So these are all properties that you'd like to be able to support, and obviously these things can't be supported by a single system. If you take something like Hadoop and you compare it and you say, does it satisfy all these things? No. If you take some kind of real-time system and you compare it to all these things, does it satisfy them? No. So the point I'm making is you can't just take what is counted as a big data technology and put it down and say, right, I've got a big data architecture. It fundamentally won't be fault tolerant, it fundamentally won't satisfy even half the criteria that you'd like to have as part of a big data system. All right, so I'm going to quickly talk about what is Storm, so you guys have got a bit of context, and then I'm going to come back to where does this thing fit inside big data architecture? How does it help us satisfy the criteria I've just discussed? All right, so Storm's a distributed real-time processing engine. It was originally built by a group called Backtop, Java Nathan Mars. They got bought out by Twitter, I think, 2009, and Twitter then open sourced the framework. Obviously, from their point of view, they're selling revenue in terms of advertising, so they're just trying to get more developers involved so they get essentially free development skills. Twitter themselves use it to drive their advertising revenue, so being able to understand where URLs are flying around the Twitter space, around the Twitterverse, and how can they charge for these things. So Twitter supports a broad range of use cases, so you can use it for complex word processing, you can use it for stream processing, you can use it for distributed remote procedure calls, you can use it as a real-time layer of big data architecture. It supports transactional semantics. So this is not transactional semantics in the sense of XA or two-phase as you'd expect within a relational database sense. This is more generic and it can be achieved on top of the relational database. It can be achieved on top of the file. It can be achieved in various ways. It's robust. Polyglot, the current set of languages that you can use to deliver Storm with: Ruby, Java, Clojure, Scala. I'll show you, I've got some examples using C++. So wide range of technologies that you can use. And to a large extent with open source, you want to be able to use different technologies because there's a particular framework you need to use. It's written in Scala or it's written in Java. You need to be able to use it. And then low latency. So just to define what low latency is here, in some applications low latency means sub 5 seconds. When I talk low latency here, I'm talking millisecond latencies, and I'm talking volumes of 1 million transactions per second. Okay, so there's some fairly good benchmarks upward to 1 million transactions per second. And that's talking 3 to 5 large AWS instances. All right, so the current set of use cases where people have this thing in production, obviously going to be Twitter. Groupon use it for a large portion of their data processing. So various queries coming in, doing real-time processing in the way that we typically expect people to use something like Hadoop for. They're using Storm. The Weather Channel, similar sort of thing. You've got all of your data streams coming in from what are essentially sensors. How do they correlate that data? How do they get it up and display it correctly for you guys to consume? InfoChimps is an American organization who are fairly well known in the big data space, and they use it as the real-time layer as part of their big data architecture. Aries Communications does real-time comms machine to machine, so they support sort of GPRS chatter between sensor devices, intelligent equipment within vehicles, those sorts of things. And one probably a lot of you know is Flipboard. A lot of their content delivery, a lot of their stream processing is done in Storm. So it's not only specific to Twitter, it has supported a wide range of use cases. I think there are about 45 companies that have advertised production instances of it. We've got 2 customers that we've delivered into production on Storm. So yeah, it's not that it's an open source technology that you've got a particular risk about implementing. It's only on version 0.8.2 at the moment, but well supported in production. Alright, so the basic concepts in the Storm world. The first thing is called a tuple. So this is a way to represent data. Essentially it means a list of named values, and they can be of any type, so it's dynamically typed, and it is delivered in Java, but the fundamental of a tuple is dynamically typed. Okay? A stream is an unbounded set of tuples. So for those who know, for example, Hadoop, you think about records, there's potentially tuples as well if you're putting something like cascading on top of it. It's a very similar concept, except in the Hadoop and in the batch world, you've got a bounded set of tuples. In the Storm world, the stream is unbounded. It just continues forever. There's no start and end point to it. A spout is a source for a stream, so it's a way to get information out from an external system, be it a queue, be it a database, various means, but the spout is the fundamental way that you get data into the topology. A topology is a collection or an arrangement of spouts and bolts that deliver certain value. A bolt is where all the actual processing happens. You can use filtering functions, aggregations, joins, writing out to search engines, anything you can think of, anything you can code, you can put inside a bolt. Alright, the tasks and the workers I'm going to go into in a little bit more detail. So the way that you achieve parallel processing in Storm is that it uses the same clustering management technology as Hadoop, the Zookeeper, and it puts together a bunch of worker processes, and a worker process exists on a particular node, and you can have many executors, and the executor runs a task. A task is a particular execution of a bolt or a spout. Okay? So you've got many nodes, you've got many worker processes on the nodes. The worker processes can have many executors, and executors are time-sharing tasks. Okay? So you've got many layers of abstraction in terms of parallel processing. It's all very lightweight in terms of the way it communicates with each other. It's 0MQ in between, and you don't expect that to be, it's low latent and it's low overhead, it's really lightweight. Okay. So you can quite easily specify that I'd like to have a couple of hundred instances of a bolt around the cluster, and it'll take care of distributing the work to those various workers, and you've quite easily got some parallel processing that way. Okay, so how do parallel streams work? You've got a set of spouts getting your inputs, and the tuples then go as part of the stream off to one of the bolts, and the bolts get wired together as part of the topology definition. Okay? For each layer that I've represented here, it's a definition of the bolt, and you can have as many instances as you like. The way that the bolts communicate to each other, the bolts don't know about downstream bolts, they only know about upstream, and you can define the way that these communicate with each other. For example, you can say, I'd like to have a round-robining algorithm. So every time the bolt emits a tuple, it's going to go around robin to all the downstream bolts, and therefore get an even distribution of the load across all of those workers. The other approach is to say, well, a certain bolt has got some kind of implicit state in memory, for example, and I'd like all of the tuples that relate to this particular field or this particular piece of information to go to that particular bolt. You can then ask the topology to group by that particular field, and all of those tuples with a hash mod will end up at that particular bolt deterministically. Okay? And that's between deployments too. Okay, so that's just talking to the grouping. This is representing effectively the round robining, what they call a shuffle grouping, but you can quite easily specify that like a global grouping, which says it's going to go to all downstream bolts. Or I'd like to do a field grouping, so specific information to specific bolts. Okay. So for those who are familiar with an actor model, it's very similar to an actor model. It's not a true actor model, but a lot of the concepts are shared. All right, so with those couple of concepts out of the way, let's dive into a bit of code. I'm correct in saying that this is a technical group, so I've put a fair amount of code in the presentation. If you see anything there, you're welcome to just ask me what it is, a bit more information, it's fine. So this is the Java API. And essentially what you're looking at is the definition of the topology. So don't think about it in terms of string, and don't think about it in terms of procedural imperative programming, think about it in terms of declarative in a Java DSL. So you've got a topology builder, and what you're going to do is declare what are the different pieces of functionality you provide. So from the top there it says builder set start. You're going to give each start or each stream an ID. So for example at the top there is log start, and I'm going to create a new instance of log start, and the 10 is defining how many parallel instances of that I'm going to have to quote across the cluster. Okay? I'm using the term topology and cluster fairly interchangeably at the moment, but in a real sense, you've got a Storm cluster, and a Storm cluster can hold many topologies. Right. The bolts then, essentially, the second line there, I'm creating a new log rules bolt. So what this thing is going to do is going to consume a tuple, it's going to execute a set of rules, in this case being performed by rules, and it's then going to emit those via a shuffle grouping to an indexer on the third line. Again, 10 instances of it around the topology. From there it's going to go off to a counting bolt, which is going to emit that into a Cassandra bolt, which is going to store it as a count into Cassandra. So what you're getting here is effectively a stream of log entries coming across into the cluster. You're going to get some filtering and some rules executing on those, so it's an intelligent dealing of that. You're then going to index them, in this case, into Elasticsearch, so that I can search them and get statistics on this later. And then just to show some basic statistics is to do a count on a particular value and store that in Cassandra as a running count. In this particular case, using a count column in Cassandra. Right, so the end result here is that effectively you get this view. So those who know Logstash and know Grafana, this is a standard instance of Grafana. The difference is if you were using Logstash and Grafana, you can only deal with a very small value. With this, and you also can't centralize any logic and rules and processing of the logs. So this topology would leverage something like Logstash as a log agent, but then centralize the rules execution, centralize the processing and control of the logs into a single place, being the Storm topology. And the net result here is that you'd be able to search and view and get statistics of all your logs in real time. So just to go through how the Spark works. There's obviously a lot of boilerplate code in Java. If you use the Scala or the Clojure API, a lot less boilerplate, but yeah, I'm kind of assuming there's more Java developers in the room. So ignoring the boilerplates, the key thing is that you've got this method called nextTuple, which gets executed by the topology as often as possible. And all you're going to do is read off somewhere and emit the values that you've read as a tuple into the topology. So in this particular case, if I'm not mistaken, yep, so just have using a Redis publish subscribe queue, pass the information into a JSON object and pass that into a log entry and emit that onto the cluster. So at the bottom, essentially the log entry is now a well-structured object. There's a serializer defined to get that serialized onto the topology rapidly, and that gets emitted as a tuple for a downstream bolt to process. Right, the bolt has a single, again, there's lots of other boilerplate that I'm not showing, but you have this one essential method being execute. It gets passed in the tuple, and all it's going to do here is extract the value and pass that off to a knowledge session, which is executed in rules. So you've got a stateless knowledge session being bound to each bolt. So it's quite performance and it scales very well. And from there, there's a set of rules that are going to execute against the tuple, and you're going to get some defined behavior. The reason you want to execute it in the rules is that you can define declarative rules, but then also you can externalize your rules logic into something like a rules manager, and you can change the way the cluster behaves at runtime. So to give you a quick idea of what the rules look like, for those that are familiar with the rules, it's a fairly simple when-then kind of ignoring the salience, etc. of the rules. So there's two there, so I'm going to filter by type. So if I see it's a particular type, I'm going to set the filter on the log, and then it's either going to get thrown away or it's going to continue processing further to downstream bolts. I'm also going to do some extracting of fields. I've set the salience higher so it can run later. And all I'm going to do is just use a regular expression pattern. I'm going to extract some more fields, and I'm going to add those in there. So, you know, it's a fairly toy example in terms of logging. I could have executed a lot more logic there to say, I've seen a certain number of errors, and I can keep a count. and I've seen a certain number of queries of a certain type, that means execute some action. And I could do that within the Visual Tools session, have those tuples a bit downstream, and execute some of the logic on the topology. So it's just to give you an idea of the kind of things that you can do. This one is going to index the log into the Elasticsearch cluster. So this is what Kibana would essentially provide presentation layer for. So it's just going to extract the fields it needs, and it's going to call the client API for Elasticsearch. Alright, so coming back to some of the concepts that I wanted to graph out and talk about. First one being immutability. So why is immutability key? You can't, first of all, from the scale point of view, it's difficult to deal with mutable state when you're doing parallel processing. In this STB, that you have to then synchronize the value or share the value across all the different executors, which is not only complex but also kills performance because you've got to have necessary locking involved. So immutability is important from the scale point of view, but then also from a data flexibility point of view, but also from a fault tolerance perspective. Again, bound complexity, you want to try and limit the amount of places where you're doing particularly complex things. Stormwind of itself is actually a fairly simple framework. It is fairly robust. You can make it complex if you want, but it's one of the concepts you really need to think about. When you're doing real-time processing, a key one is understanding what your state is. So there's going to be a lot of cases, especially if you're doing low latency concerns, where you've got to keep your latency down entirely, and you can't then be talking to a database at any time or disk at any time. So you're going to be keeping in memory state. You're going to make some of these bolts stateful. It's not persistently stateful, but it's stateful for some period of time in memory. And when you're doing these kind of things, you've got to take into account whether your state is commutative or associative. What I mean by that is, does the order matter? So, for example, if I said 5 plus 5, it doesn't matter what 5 plus 4, it doesn't matter which order I do that in, 4 first, 5 first, it's going to land up with the same answer. However, if I do division, the order does matter. Okay, so the nature of your state in terms of events is something that's important to understand, because that subtle difference allows you to scale and gives you a stable system or not. And the way you design your topology is very dependent on that. Partitioning, so just thinking about CAP theorem, how am I going to partition in terms of, so how am I going to subdivide my data sets when I have to do things like sharding, etc. What is my concerns around consistency? Do I really need strong consistency? Can I get interventional consistency? And then obviously for these kind of things, it's often about time series data, so just being concerned about what time means on your data is often far more important to think about on the real-time concerns than on the batch concern. Right, so coming back to where Storm fits in here. This is an adaptation of the Lambda architecture. The Lambda architecture is a lot simpler than this. The Lambda architecture is something that was proposed by our mate co-op Storm, being Nathan Marks. He's also got a book coming out on it fairly soon, but essentially it says that you've got a batch layer where you store all of your immutable states and you're able to compute views, but the views are fundamentally throwaway. I'm quite happy that I can always recompute my view if I lose my data. The only thing I'm interested in is storing my immutable data in a safe location. And I can pre-compute a certain amount of data within my batch layer, and the idea then is that I can combine those pre-computed views with some kind of real-time layer in order to make these things not only fault-tolerant, fundamentally immutable, but also performant in that I can get low latency responses by combining my current data, so the data that's in flight now, with my batch pre-computed views using some kind of real-time system, in this case Storm. Okay? So I can ask a question of this kind of architecture, like, I'd like to know what my sales data looks like for the last 10 years, and it'll be able to give me an aggregate view of that, including the last 10 seconds, or the last second. Okay, this thing starts to become fundamentally powerful, not only in that you can ask that kind of question and get that kind of answer, but over time you can ask any kind of question. So because you've got entirely immutable states in the batch layer, any question you want to ask, you can create a computed view to be able to answer that question. So it's not like having a predefined data model, where you can only ask questions within the constraints of what that data model is, saying, I've got the entirely immutable view of the facts, of the input facts, and therefore I can pre-compute any view I like on that. So in that space, you think about things like Hadoop, to an extent, depending on your performance requirements, things like Spark. So it's file management concerns, it's abstractions on top of MapReduce like Cascadog, Cascading, Scalding, Scooby. In the analytics space, things like Encanter, Reka, Nahat, and R. I've explicitly separated out the concept of an analyst here and made it part of the batch environment because the actual analytics task is not something you do in the real-time layer. The real-time layer is there for operational analytics, so you've already gone through the analysis process, you've already done all the clever things, and you've come up with what is an operational model, and that's then deployed in the real-time layer. In the middle there being the services layer, that's essentially a place where you'd like to have, as you won't be able to access the views that you pre-computed in the batch layer. So typically you'd like to have a pure read-only view or a read-only database in that case. So things like ElephantDB, but depending on your operational environment, you might want to only have a single NoSQL database, and then you might leverage something like Cassandra in that case, because you've got other places where you want to have some temporary mutable state. And then off to the left, you've got your various data sources. So what this architecture satisfies is that it's fundamentally fault tolerant, it's fundamentally mutable, it's real time, it scales, and over time, I can evolve what is the kind of data that I'm looking at, I can evolve what are the kind of questions I need answered without having to worry about the constraints of my data model that I had to define up front. Okay? So if I've got a situation here where I do a release and I've got a bug in my code and it destroys one of the views, doesn't matter, I delete the view, I roll back, I recompute that view and I continue. And at the most I've lost some short period of processing time, but I definitely haven't lost my data. Okay, so we get deterministic mean time to recovery, all those sort of concerns. And bear in mind, when you get onto these larger data sets, these kind of things become extremely important. When you've got a mean time to recovery of an hour, and you've got a petabyte data set and it's mutable, and you have to rebuild that, you're not going to meet your MTR. Okay, so from an IT operations point of view, from an availability point of view, it actually starts to become essential, especially as the volumes and the sizes get larger. Alright, so in the Hadoop world and the MapReduce world, there's been a series of what are appropriate abstractions that have been built on top of MapReduce. And I say that because MapReduce is not necessarily an intuitive way to think about data processing, not for everyone unless you come from a functional background, but also it's not a very productive way of dealing with data. So if you think about writing a Java MapReduce, anything is going to be upward of 100 lines of code for even simple things. So creating abstractions on top of that allow you to reason about your data in terms of the data pipeline, and to be productive in the way that you deliver those pipelines is quite important. So things like cascading does this. It gives you the ability to build pipelines on top of the Hadoop that generates the MapReduce for you underneath there. And then there's DSLs that have been written on top of it in the Scala world, Scalding, in the Clojure world, Cascadog. Okay. So the reason I'm bringing this up here is to draw a parallel between what it means to have a reasonable abstraction in the batch world and what it means to have a reasonable abstraction in the store world. So just to talk about a reasonable abstraction in the batch world, this is Cascadog code. These are two Cascadog queries. I'm assuming there's not that many Clojure developers in the audience, so I'm going to just talk through the query quickly. The function, so this is a list, meaning that everything is a list and the first entry in the list is the function, simply. The arrow on the left-hand side is a execute query, and what comes in the vector immediately following it is the list of output fields. So if you look at the top one, I'm going to do a word count, and I'm going to output the word and the count. The next line specifies where I'm going to get my source from. So you'll see it says source, and it's got a question mark word, that's essentially my input field. Okay? Then I'm going to execute some other function, which is essentially, if you think about it in pure data terms, it's just a predicate. And I'm going to execute some kind of predicate. It can be a function, it can be a filter, it can be some kind of aggregate, whatever you want it to be. And that's going to execute on every single tuple within the data pipeline, which is an input based on your standard batch process. Okay? So if you were to do the sort of canonical word count in MapReduce, what is it? I think it's about 80 lines of code in MapReduce. That is the exact same example in 3 lines of code. Okay, so Twitter also use Cascadog to try and query the entire Twitter data set, and they can ask questions like, I'd like to know all the people who are female and younger than 30 who are following someone older than them. 3 lines of code. And they get back an answer from their entire data set without ever having modeled that kind of relation within the original data model. Okay? So it's an extremely powerful way to reason about extracting, querying, manipulating data, because you're thinking in terms of a pipeline and you're thinking in terms of predicates which act on data. The second one there is computing. Sorry, is someone asking a question? The second one is also executing a query. I'm going to output a document ID, a term frequency, and a term count. Okay, so this is potentially a portion of something called TF-IDF, which I'll get to just now. But essentially, I'm going to do a count on certain terms coming through from the data. Okay, so this is an abstraction on top of MapReduce. The abstraction in the Storm world is something called Trident. So I've spoken about what is a set of sparks and bolts, which is your low-level primitive processing concept in Storm. There's also a high-level abstraction called Trident. And Trident also allows you to think about how I'm processing my data in terms of a data pipeline with streams and aggregates that act on the tuples as it flows through that stream. Okay? So again, it allows you to reason about it at the correct level of abstraction, but it also means that you're going to be more productive for the particular thing that you're doing. So this is again the word count example, and what it's going to do here, so again this is closure, it's defining a bolt, it's got the execute method, and it's going to take in each word out of the tuple, and it's going to do a count, and then it's going to emit that and act it. Okay? So again, instead of coding a whole lot of functionality to say I'm going to extract a word out of there, I'm going to count against some rather mutable variable I've got in memory with the word plate associated with that, I can define a processing pipeline and a predicate, and it happens against a stream instead of a batch set of data which is flowing through a pipeline. Okay, so I figured probably it would be a good idea to bring that back down to earth in terms of Java. What you'll notice, the DSL that you use for Trident, whether it be in Clojure or Java, is actually pretty terse in either case. And that's fairly uncommon for Java, obviously. So again, it's declarative and it's quite terse, and it feels very similar to a functional DSL. And what it's doing here is it's going to split a word into a set of sentences. So I've got a stream, I've got a sentence coming through, I'm going to split that, and I'm going to emit a set of words to a downstream function of some kind. And what I'm going to do here is I'm going to do a count aggregate, and I'm going to store that value into some kind of state. So the state here can be anything. It can be in memory, it can be a NoSQL database, it can be Hadoop, it can be whatever you want it to be with certain adapters applied underneath. And so again, it allows me to think in terms of a processing pipeline, and then I can also start to introduce persistent state against functions or against aggregates. Alright, so the example I'm going to give you here is TF-IDF. It's a bit small, but this is a function for term frequency and inverse document frequency. This is a trivial but fairly important thing in text mining, is to say I'd like to understand for a particular document what is the relative importance for each term within that document. And the way you figure that out is you count the number of instances of the term within the document versus how many times it occurs in all the previous history of documents, so in a given corpus. So, on the face of it, when you look at the set of functions, it looks relatively complex. If you think about it in terms of a data processing pipeline, though, it's quite simple. I'm going to fetch a document, I'm going to tokenize the document, I'm going to filter out which terms I don't want. So, use a stemma, a set of stop words that I don't want, so I can filter out which words I'm not interested in. I'm going to then group by the source, and I'm going to count that, and that's going to be my total document count. Okay? So all I've done there is said I'm going to filter out, or I'm going to do a group by, so that's a single predicate, and then I'm going to do a count. So literally 2 lines of code, I've now got a count for all the documents. On the next stream, I'm going to do a group by the particular term, and I'm going to do a count again, and now I've got the document frequency. So I know how many times a term has occurred in all the previous documents. I'm going to do the same thing now, but I'm going to group by term documents, and that's going to give me the amount of times the term has occurred in this document that I'm dealing with in the stream. And I combine those three things together in a function which is simply an expression, and I've got TF equals data. So what seems like a relatively complex thing, when you reason about it in terms of the data pipeline and predicates acting on data, becomes fairly trivial and becomes highly scalable. So you can do this at massive scale, and you can play with how you want to parallelize it. Alright, so a couple other things just in terms of predictive analytics. I mentioned it earlier, but you don't consider something like Storm as a place that you would do the actual analysis phase. I mean, it's something where you would do the analysis phase up front, and then you would create your operational model and deploy it to something like Storm. So this is an example straight out of R. It's one of the base examples in R. And you can build a model, a classifier, and you can deploy it into Storm and have it classify streams based on what you've built in the model already. Okay, deployments of these things. The out-of-the-box deployment is supported by something called Pallet. It's a closure-based operational framework, so it's like Pallet or Chef, Puppet or Chef. So it's up on GitHub. It's a two-line exercise, and you've got an AWS cluster. There's a configuration file that you can specify how many nodes, how many workers, etc. And you execute these two commands, and you'll get a cluster up on AWS. It works very nicely. It's got all the baseline controls in terms of user permissions, user management, firewalls, all of that, so you take that as a whole. Alright, so the community itself, between 0.8.2 and 9, focused on improvements on the Storm GUI to a large extent. The Storm GUI is not the most attractive thing, but it's functional, gives you a good idea of what's going on inside the cluster. Locally here, myself and my team are going to be focusing on real-time predictive analytics and some integrations with R. And we will be contributing those things back to the community, so if you're interested in getting involved, come chat to me. Alright, other options. It is open source, so you always need to consider these things. Depending on what your latencies are, you can consider something like Spark. There are use cases out there in the world where people only had 1-2 second latencies, and so they used Spark as part of their online web application where what is suspiciously a batch query is initiated by a web request, and the response comes back as part of that batch process. So if your data set is small enough, within the memory of a cluster, 100 gigs or less, something like Spark, if you don't have that much low latency, is also a viable option. S4 from the Apache guys, Akka in the TypeSafe and Scala world. So there's various other options. You've got to take into account various factors, but it's worthwhile mentioning what the other options are relative to Storm. Okay, so if you want more information, the Storm project is the web page. The GitHub page is on Nathan Mars' GitHub account. The context in terms of big data is originally an article we wrote on his blog called Beat the Cap Theorem, to talk about how this fits into big data architecture, what immutability means, and what Storm brings in order to achieve that. Cascading, if you want to go and have a look at the batch abstractions. I've got various contributions to Storm on my GitHub page, and then Michael Knoll is one of the Storm community members who's written a lot of good blog articles around understanding how the parallelism works, how Trident works, etc. The presentation, if you guys want to refer back to it later, I've deployed it up on S3, so you can go and have a look at it. It's there at the moment, and that's the URL. Alright, so I think that's it from my side. Hopefully what you've gotten from this is where Storm fits in. You've got an idea of some of the use cases. You won't necessarily be able to write code, but you've got an appreciation of the fact that it's relatively simple, as long as you've thought about the design concepts. And hopefully what you can take away is to look at your current architecture and say, am I still doing things the way I always did things, just at a much larger scale and therefore in a much riskier way? Any questions? Yep.
Back to the architecture slide. So I just can't understand how you actually start on you say you've got these pages on this.
Yep.
And then you say you want to request stuff and web request in the log entries for the
batch process. So does the topology kick off when you do the batch query? Does it happen when the web query happens, etc.? So a topology fundamentally exists forever. It's not supposed to have a start and end points unless, of course, you've got operational issues. So it's always waiting for input. The batch views that I talked about are pre-computed and are waiting around as state to be queried. Okay? So if you get a web request coming in, it comes in as an asynchronous event into the topology, and the topology will then use certain fields out of that event to go and query the state, which is the batch pre-computed view. It will combine that with the real-time state and it will return it. Okay, so
none of the spout you're talking about, that's actually, the input for that spout is actually a web request essentially?
it can be a web request, it can be a JSON endpoint, a RESTful endpoint.
It's a request, not like a real-time log or something, it's actually a request.
It can be either. So you can, the two approaches you can look at it as, I'm doing events, stream processing. So I've got a constant stream of events, and I'm simply updating states, persisting states, doing some computational against that stream. The other way of looking at it is that I'm going to issue requests and I'm going to get responses. So Twitter uses this for computing the reach of the URL. So they query Storm and they say, I'd like to know how many people have seen this URL. And it will go and query the various data sources in parallel, consolidate that answer and return it back in real time. So that's called distributed remote procedure calls. And you create the topology in very much the same way, except that you've got a DRPC server which consolidates the outputs of the streams and returns it to you. So from the outside world point of view, it's a synchronous call, but actually what's going on is a whole lot of parallel asynchronous under the covers. Okay. So, and especially in the case of Trident, you would model a data stream, and some event is going to kick off that data stream or a particular tuple within that data stream, and it's then going to query state which exists somewhere else. So you might have an aggregate view sitting somewhere else. You can query that as part of your stream flow, aggregate your stream, and return it. Does that answer the question? Further questions, guys? Thank you very much for the time.